So we've now learnt to calculate the derivative, we've learnt to do it term by term, and we've also learnt the three rules: product, chain and quotient rule. Now we're going to do actually how we use the derivative. We've learnt the skills of it. What's it actually used for? Well, if you think about just a basic curve, and let's say it looks something like that. It's used a lot for curve sketching. So we've got some curve on the Cartesian plane, and I want to be able to sketch this curve. So the first points I start with, try and find, are what's called the stationary points. Now this is going into Year 12 work a little. However, at the stationary points, the tangents are drawn there and there, and the gradient of those tangents are 0. So if we can find the first derivative and make it equal to 0, we'll find the x-coordinate that corresponds to these stationary points. If we find the x-coordinate, we can sub it in to find the y-coordinate. So it will give us 2 points on our curve. We can also go and find the x-intercepts and the y-intercept. And then later on, which is Year 12 stuff, we can then find, is it a minimum or is it a maximum? So the first thing we're going to do though is to find the value, the gradient of a tangent on some part of the curve. Okay, obviously at the stationary points it's 0, but we might pick, let's say that's the point 3. What's the gradient of that tangent at the point 3? And we also talk about the normal to the curve, and the normal is the line that is perpendicular to the tangent. So our method is to find the value of the gradient of the tangent first, and then it's perpendicular, so we find the negative reciprocal of it. Okay, so we've got our first example. Find the equation of the tangent to the curve y equals x squared at the point 3 and 9. So if we draw ourselves just a little sketch, we know that's a parabola, vertex 0, 0, and the point 3 and 9 might be somewhere there, doesn't really matter. The question is asking us, what is the equation of that tangent? What's the equation of that line? Now we know how to find the equation of a line using slope-intercept form. So we know we need to use y minus y1 equals m into x minus x1. And what do we need? Well, we've got our point. We've got the x1 and y1. x1 is 3 and y1 is 9. What we need to find is the gradient. And in the linear functions chapter, the way we found that was using 2 points and using the gradient formula. However, this time we only have 1 point. And so you know that this is where differentiation comes in. If we derive the function once, we get the derivative or the gradient of the whole curve, and if we sub in the particular value we're given, the 3 here, we'll find the gradient of the tangent at this particular point. So we've always got to be given an x value. We might be given the 2 values, we don't really need the y at this stage, but we need the x value. So our solution, we know we need this formula here. We've got x1, we've got y1, we need m. To find m, we get the derivative. So dy dx of the whole curve is 2x, but I don't want the whole curve. I want it only at the point x equals 3. So at x equals 3, m equals 2 times 3, which is 6. So the gradient of this line here is 6, which fits the diagram. It's a positive gradient. And so with the 6, we can now fill out this formula and find the equation of that tangent. It's just a straight line. So it's y minus 9 equals 6 into x minus 3. Y minus 9 equals 6x minus 18. Let's put in general form. 6x minus y minus 9 equals 0. So what we've found, this equation here, is the equation of that tangent at the point 3 and 9. If we were to choose another point on the curve, we'd get another equation, clearly. Example 2. Find the tangent equation, or the equation of the tangent, at the point 1 and minus 1 on that particular curve. Now again, we've been given an x value. The gradient's not dependent on the y value, we need the x value. So the tangent equation, doesn't matter what this curve looks like, it's not as easy as the last one, but we're finding the equation of a straight line essentially. So we need the equation y minus y1 equals m into x minus x1. We've got our points, our x1 and y1, we just need our gradient, and that's gained from the derivative. Now if you have a look at this, it's not a simple differentiation this time. We've got a fraction, so we probably need to use one of our rules unless we can simplify it. And I don't know that we can. Doesn't look like there's going to be a common factor, and we won't be able to cancel out anything. So out of the product rule, when you've got two terms multiplied or two expressions multiplied, the quotient rule when you've got a fraction, or the chain rule when you've got brackets and indices, which one do you think we're going to use? Correct, it's the quotient rule. Okay, we've got a fraction. So out of the fraction, we get the fraction. So let me write down the rule for you. Remember it had u's and v's in it. And it was vu dash minus uv dash all over v squared. So to derive it using the quotient rule, I suggested to write out what your u and v are, what your u dash and v dash are. I might just rub that out and move it down a bit. And then go from there. So u equals 3x cubed minus 6x. Therefore u dash is 9x squared minus 6. And v, which is the denominator, equals 8x squared minus 5x to the fourth. And v dash is 16x minus 20x cubed. So plugging that all into the formula, vu dash minus uv dash on v squared. It's not a waste of time writing all this down because now it's very straightforward. So v is 8x squared minus 5x to the fourth times u dash, 9x squared minus 6 minus u, 3x cubed minus 6x, and v dash 16x minus 20x cubed. Just fit that there. All over the bottom squared, v squared. So 8x squared minus 5x to the fourth. Now that's quite a complicated, long derivative. Do we want to expand that out? We don't need to. The question isn't asking us find the derivative in simplest terms. It's not leading on to another question. All we need to do with that is to substitute in the value of x, because this is the gradient of the whole curve, but we only want it when x equals 1. So all we need to do is sub in the value of x equals 1, which is very easy. We don't need to expand it out. So if x equals 1, we've got 8 minus 5, 9 minus 6, minus 3 minus 6, 16 minus 20, all over 8 minus 5. Oh, that's squared. Okay? So finally we have that m equals 3, 3, minus 3 minus 4 all over 3 squared. Just going to rub it out, make that a nicer 3, and minus 3. It's better. So m, when x is 1, equals 9 minus 12 on 9, which is minus 3 on 9, which is minus 1/3. So solving it into y minus y1 becomes y plus 1 equals minus 1/3 into x minus 1. Don't forget the point was 1 and minus 1. Times everything by 3, that's 3y plus 3 minus x plus 1. So if we change that into general form, that's x plus 3y plus 2 equals 0.